Hello, we're going to discuss the last section of Chapter 13, which is about Le Chatelier's principle. Okay, so let's look at some things that we've talked about, factors that control the position of equilibrium. So these factors are really important. It's important to know how they affect the equilibrium position so you can make predictions about what's going to happen in your reaction. Okay, and if you work, in a chemical process or an engineer, usually we're trying to produce things, so we want equilibrium to lie really far to the right. We want to produce products. So we can look at factors that affect position. We can kind of manipulate the position to produce products like what we want. So we use Le Chatelier's principle to predict the effects of changes in concentration, pressure, and temperature on the system at equilibrium. So we're going to look at those three things. Basically, Le Chatelier's principle says that if a change is imposed on a system at equilibrium, the position of equilibrium will shift in a direction that reduces that change. So that's kind of the overarching idea. So if we keep that in mind when we're looking at these three factors, hopefully that will help. So let's look at concentration first. Okay, let's look at the synthesis of ammonia. So we've got these equilibrium concentrations. Okay, and let's say that we change the concentration of the N2. Okay, so we're looking at adding N2 to this process. Well, if we want to determine the direction that the equilibrium is going to shift, we need to calculate Q and then compare that to K. All right, so our Q value is going to equal the concentration of our NH3. And if you remember this equation from previous, the NH3, it's 2NH3, so that's getting squared. Concentration of N2, which is on its own, and then H2, sorry, and that's getting cubed. Okay, and these, because it's Q, these are initial concentrations. Well, if we're adding 1 mole of N2, then that's going to change our initial concentration of N2. And so this is going to become, let's see, NH3 is 0.202 molar. N2 is now 1.399 molar, and H2 is 1.197, and that's cubed. Okay, so if you calculate this value, you should get 1.70 times 10 to the negative 2. Let's compare that to our K value. Now here we haven't been given Ks, we're going to use equilibrium concentrations. So our NH3 is 0.202 squared, divided by our N2 is our equilibrium, which was our 0.399, and our H2 is 1.197, and that gets cubed. Okay, because these are equilibrium, it's at equilibrium, then we added the N2, and we looked at the new shift, the Q value. Alright, so our K for our initial equilibrium is 5.96 times 10 to the negative 2. Okay, so here Q is less than K, and so that means that the equilibrium will shift to the right because we're trying to reduce the change. Okay, according to Le Chatelier's principle, the equilibrium is going to shift in the direction that reduces change. Because we added N2, and N2 is a reactant, we're going to shift to the right to try to produce more products and kind of get rid of that change. Okay, so let's go over that one more time. If we added N2, we would increase the number of collisions between N2 and H2. So that's going to increase the rate of the forward reaction, so it's shifting to the right. Okay, well, if we have the forward reaction being increased, now we're going to increase the rate of formation of NH3. Which is then going to increase the rate of the reverse reaction. So we're going back and forth, until we reach a new equilibrium position. And so we're looking at the effect of concentration. Okay, so if we use Le Chatelier's principle, the change was we added N2. Okay, so we changed that concentration. This means the system is going to shift in order to consume the N2. So it's going to shift to the right. And if we added ammonia instead, so if we added a product, the equilibrium would shift to the left. So it's trying to reduce the change, whatever direction that is. So in general, if a component, either a reactant or a product, is added to a system already at equilibrium, the position will shift in the direction that lowers the concentration of the component. So we added a reactant, it shifted to the right. We add a product, it shifts to the left. It's trying to reduce the concentration or reduce the change. If a component is completely removed, it's the opposite effect. Okay, so we added into, it shifted to the right because we had more. If we remove something, it's going to shift to increase that concentration. And so if we decrease a reactant, it's actually going to shift to the left to increase that and reduce that change. If we decrease a product, it's actually going to shift to the right in order to produce more product. So it's going to try to reduce the change however possible. All right, let's look at change in pressure. There are 3 ways to change pressure. You can add or remove a gaseous reactant or product. You can add an inert gas, which is not involved in the reaction, it's just present. Or you can change the volume of the container. Well, we've already talked about concentration. So adding or removing a gaseous reactant or product, we've kind of covered that already. Adding an inert gas is going to change the total pressure, but it won't affect the concentration or the partial pressure. So it's not going to affect equilibrium. It's not included. We're not going to talk about it. So that leaves the third one, which is changing the volume of the container. Well, changing the volume changes the concentration or the partial pressure if we're talking about gases. And so that is one that we want to look at. So when the volume of a container with a gaseous system is reduced, the system will reduce its own volume. And so the way it does that is by decreasing the number of gaseous molecules in the system. And so if we look at the ideal gas law, we can see how these two are related. At a constant temperature and pressure, volume is proportional to the number of moles. So by reducing the volume, we're reducing the number of molecules or moles, concentration. So if we take a look at our ammonia equation again, if we reduce the volume, we want to reduce the number of molecules. Well, here we've got 1 mole of N2, 3 moles of H2, so we have 4 on this side, 4 moles or maybe 4 molecules. On the reactant side, on the product side, we only have a total of 2 molecules. So if we reduce the volume, we want to reduce the molecules. It's going to shift toward the products because it contains less molecules. The opposite is also true. If you increase the volume of your container, we would go towards more molecules, and so it would shift left. All right, let's look at temperature. So all the changes that we've looked at so far alter the equilibrium position, but not the equilibrium constant. Okay? A change in temperature, however, does affect the equilibrium constant. So let's take a look at our ammonia equation again, except now we are adding energy. So here energy is a product. Well, if you're adding it to the system like this, position of equilibrium is going to shift in the direction to consume the energy. So if we're adding it as a product, we're going to shift to the left to reduce that change. So by shifting it to the left, we're going to decrease the concentration of NH3 and increase the concentration of N2 and H2. This is going to decrease the value of K. And so and this would be for an exothermic process because you're giving off heat at the end. For an endothermic reaction, it's the exact opposite. Okay, and so K would be increasing instead of decreasing. And so really the best way to handle temperature is to treat the energy as any other reactant or product and then determine the shift just like we did with concentration and pressure. Okay, so here are some problems to work on and we'll cover a few examples in class. Have a good day.